Hi, everybody. Thank you for joining us. So we will wait a couple of minutes for the rest of the participants to join us. So to avoid any background noises, we've muted everybody for the session, but near the end of the workshop, I will turn on the unmute function for if you have any questions for Prof. Lee when he has finished his presentation now. So we will have about 5 or 6 minutes at the end for Q&A. Although during the course of the talk, if you do have questions, please feel free to put it in the chat and I will prompt Prof. Lee to look at the question in the chat during the course of the presentation. Okay, so it's already 3 o'clock, so we'll get started. So I'm Su Yan, I'm the coordinator for the Researcher Unbound workshops, and I'm very honored to welcome Prof. Lee Ping Ping, who is a visiting associate professor in the Department of Mechanical Engineering, to give his talk on smart additive manufacturing today. Prof. Lee has joined the department as a visiting associate professor, and he's currently in the additive manufacturing center. So his area of research in collaborative research in additive manufacturing and smart manufacturing. So among the many hats that he dons, he's also an associate professor on sabbatical at the University, the California State University Northridge, CSUN, and he also serves as associate director of the NASA Autonomy Research Center for STEAHM. Yeah, among many other things. So we're very honored to have Prof. Lee today to share his insights on smart manufacturing, smart additive manufacturing. So I'll hand over to Prof. Lee now.
Hey, Suyin, yeah, thank you so much for your introduction. Let me share my screen. Can you see my share screen?
Yes.
Okay, perfect. Hi, good afternoon, everyone. It's my great honor and pleasure to share some of the research that we have been done in the past. And then I think this will be a mini workshop. The purpose is we hope we can test water this one, and then we can launch the full day workshop in the future. So as Suyin introduced, right now I'm taking the sabbatical leave. So I'm the visiting associate professor in the ME department, and then I'm collaborating with Professor Fu and Professor Lu in the AM Center. And in the meanwhile, yeah, I also serve as associate director for the NASA-sponsored Autonomy Research Center for STEAM. That's why the background you can see is the Earth, because we did a lot of research collaborating with the NASA JPL, Goddard Flight Research Center, and Armstrong Flight Research Center. So I'm also the co-director for the DOE Industrial Assessment Center at the UC Irvine and the CSUN. So we did a lot of industry assessments, like 20 industry visit and energy audit for the local companies in the Southern California of the United States. And I also am the affiliate faculty in the Terasaki Institute for the biomedical innovation, because my main research area is the additive manufacturing, mainly focused on the metal 3D printing and the 3D bioprinting. And then for the smart manufacturing, so today I'm going to share more details. Can you hear me clearly?
Yes,
Okay,
it's quite clear.
Everyone know like now this is like Tesla, the mega factory production line. So I think this is manufacturing, like especially advanced manufacturing, right? And then they're coming from the industrial 3.0. And now I think we are in the era of industrial 4.0. And then the smart manufacturing, the industrial internet, right? The digital twin has been discussed a lot, right? And then, but what does it mean? And then how to implement into the advanced manufacturing, right? So this will be the scenario or the vision of the manufacturing in the future. We hope we can, so you can see this is the engine jet, right? The Aerojet engine. And traditionally, I think you can just see all these physical parts for the large component, right? But in the near future, in the vision of smart manufacturing, right? And then we see all these real-time simulation in the results and the detections for prediction. So in your either like AR environment or even the more the metaverse environment. So this will be the manufacturing. I think has been discussed a lot, for the smart manufacturing and the digital twin. So here I'm more than happy to share the digital transformation. Like in the past, the smart manufacturing concept itself is not new, right? I think a lot of people, if you're working in the industry, right, or the professors, you pretty know a lot of concept was already there back in the 1980s, for the closed loop and then for the intelligent manufacturing, right? But at that time, it's a big challenge to get the data, right? To acquire the data, collect the data, and then process data within the certain amount of time. For example, the response time, we cannot achieve like over, less than 5 seconds or the 1 second, right? Because of the limitation of computation, limitation of the sensor, and the limitation of the the AI and the connections, right? So smart manufacturing become more and more popular like 10 years ago, right? Initially, it was the industry 4.0. It was, the concept was initially brought up by the the Germany, and then they in the Hanover the axis, and then because of the advancement of sensor technology, right, like the IoT devices or the IIoT devices, and then we can collect all these data, especially in the real time or the near real time, and then cloud computing, or even now the quantum computing, right? So we can process all this data, right, in the cloud and all in the cluster, right? And then we insert really, the like seconds, and then we can get the results of to get the simulation, get optimization, and then the big data technology, right? So, and also 5G. 5G just connect like the wireless connection technology, make it possible to collect the data and then collect data from the IoT devices sensors, and then transfer, to your platform, right? And then that make it amazing, for the wireless connection. So, and also the last one is the AI. I think in the past few months, everyone was impressed by the story of OpenAI's ChatGPT, right? Like the large language modeling is one of the really good, the algorithm for the AI technology, and then they become really successful, milestone. So in the AI, and then also provide a lot of, high tech, to make it happen, right? And then to do the simulation, to do the calculation, and to the learning. right? And then, so these are the technology, development. And then from the digital transformation, you can see they got like OT, IT convergence, right? So they can do the OT better than just the IT itself, right? And then achieve like a smart manufacturing, smart factory, or the factory, the 4.0, right? And then the industrial internet, right? The IoT devices. So a lot of new services, a new business model, or even new economic system become more and more available, right? And then become more and more innovative. So from the enterprise total performance perspective, you can see they achieve a lot of the advancement from environment, and then get the flexibility, agility, and agility, sorry, and the high efficiency. So here, just give you the overall picture of the digital transformation in the past like 1.5 decades, right? How we can achieve. Here, just to show you like this one just show you, how we deal with, the big data, and then IoT, and then the smart, right? So for us, I think here just mainly focus on the data valuation collective versus proprietary and open architecture, and big data just dealing with like a business model, the data, and the practice evaluation. And then in the meanwhile, for the smart sides, right? And then that's the business of the open architecture market and the valuation, the data innovation, right? So I think in the past few years, a lot of people did an excellent job in the converting data to the information, right? Like a big data. And then also right now, because of the AI advancement, and then a lot of people trying to convert knowledge, information to the knowledge, right? But this is the big challenge now. I think our group right now also working on the few projects, right? How we can get the information to the knowledge, and then we can build a knowledge-based system, right? It's pretty easy to convert the data to information, but how you're going to achieve the knowledge is especially tacit knowledge, like 97% of knowledge is the tacit knowledge, right? And then you have to gain this knowledge by practical, the training, or the working experience, and then learning, right? So it's not easy to convert information to knowledge. So this would, and then the top level will be like how you're going to convert in knowledge to wisdom, like a human being, right? And then that will be the next level. But now I think it's still, most of them is still in this phase, like between the converting information to the knowledge phase. And then next, I'm going to share one large project we have been done in the past, working with UC Irvine, because this whole project was led by UC Irvine, and then we have the partner from like UCLA, Aerospace Corporation, CSUN, San Diego State Supercomputer Center, Honeywell, General Mills, and Tology. So this is a total $2 million grant and funded by the US Department of Energy. We have a Clean Energy Smart Manufacturing Innovation Institute. And then we have been working together to build a system. We call it the ASAP system. So it's affordable, scalable, accessible, and portable smart manufacturing solution. Because in the US, the smart manufacturing is like in the past 10 years, is not in the leading, the role in the worldwide. And then especially for the small and the medium-sized company and the manufacturers. So for the large company, a lot of them, they have the enough funding, right, to invest the IoT devices and the platform, the smart manufacturing practices into their large facility or the manufacturing factory. But for a lot of small and medium-sized manufacturing company, they cannot afford, or they don't have the right manpower or the workforces, right, to implement or to develop the related technology. So this is the why, this grant, we have a coalition of academia, small company, large company, and supercomputer center in San Diego. So we have this company working together to build a system so we can take care of the the smart manufacturing, the practices. So we call it a smart connected worker, is SCW system. And then the human is the center, the worker, and then they will be they were equipped by the different, the helmet, IoT devices, the sensors, right? And then they can talk to other workers in the meantime. So you can see here, this is the center, and then we get the real-time facility status, right? By integrating the information from the manufacturing factory. And then we also build the digital twins for the game-based virtual world training, right? And then we have the real-time, energy usage monitoring. We install the smart meter, and then we also use the AI-based algorithm like LSTM, long short-term memory, to get the energy disaggregation to get the machine stage. So, and then we also did the cognitive reduced order models for the situational awareness. So putting together, and then this is like our architecture. You can see it's the multi-sensor model, right? And then we have different manufacturing facilities, machines, workers, and the sensors. We have different like cameras, IR camera, the regular camera, and the thermal camera. And then we also have the meter, like a smart meter for power, for electricity monitoring. And then the processing units, like from like a video processing, the worker action recognition, skeleton recognition, the sensor data processing. And then we also build our own platform and the API, and then they can provide and share the data to the clouds. And then we have both edge and the cloud, the computing capacity, and then we build them. So this is the overall of this project. And then I can share more details, like from edge side, right? Besides the cloud computing that we use is the Nautilus, developed by the UC San Diego. It's open source, the platform. We can do a lot of AI training similar to the AWS, but it's more cost effective, than the commercial solution. So this is the edge intelligence our team developed, especially from the UC Irvine. And then it's the we call it e-box, is aggregating the multimodal sensor information, from like chips, from camera, from Raspberry Pi, from smart meter. And then they get the warm and then label to confirm to dialog. And then we can do the server, database, and then also showing the web visualization. So this is the whole, the like a platform model. You can see we use this edge, plug into your few sensors, right? And then they can detect your operation and the skeleton of the operator. And then this is some of the parameters for this edge box, and then the capacity. So here's the model, the cognitive reduced order modeling we did. And then like one is the PI cluster edge computing, e-box edge computing. And then we can do the optimization for the thermal simulation, right? The CG-ROM development and deployment in the computing environment. And then we also have the HPC cloud computing, where the Pacific Research Platform is called the Nautilus. And then this one used the Kubernetes for the user-friendly edge computing. And then here is another the research work we did is for the human workflow monitoring, right? Like whenever you use any operators in the facility, right? Like the worm, and then we use the open pose, right, to capture the skeleton, and then use the CNN classifier, and then to classify the different skeleton, do the labeling, and then we impose the machine map. And then in the meanwhile, we use the smart meter to collect the power, collect the electricity, right, to do the serve, and then link each operator's action to the machine state. So it's the correlation, to trying to build the correlation of the interactions and the energy usage, right? And then the phase 2 is right now, the team is working on the causality of the AI, and then trying to figure out the causality learning to figure out the more causalities besides the correlation. And then another sample we did is the instant replay. So we use Raspberry Pi and the edge computing device, from the e-box and the local memory, right? And then they connect with the smart meter. So this case, we can detect the anomaly detection, right? Whenever they saw any anomaly in the manufacturing facility, because I can show you the use case we did for the General Mills. General Mills is one of the largest food manufacturing company in the US. So their big challenge is how they're going to reduce downtime, like a 1% downtime improvement can save their $2 million, for the General Mills. So here is another example, showing the integrated nanosystem research facility installation. And then our team this is the facility in the UC Irvine, but our team at CSUN, we create this CAD model digital twin system for them. And then for these 3 rooms, and create all the facilities and equipment inside of the lab. And then we build a system to do the scheduling optimization and build the AR system. So here you can show some of the results. Like this is the one inside the facility. We also install a lot of autology, the cameras, so they can capture and then monitor the workflow inside of 3 rooms. Like whenever any machine state change and the operator's actions, they can capture, and then they can show you all these real-time information from the web-based, the API and the GUI. And then here is the augmented virtual reality for our system decision-making to see the Wi-Fi simulation, right? And then the real-time facility status, and then we build this CAD model, and then we build the integrated into the Wi-Fi simulation to get the interactions. And then you can also use the voice control to show them. So these are the examples. And then we also, at the end of the project, we did a field demonstration. The first one is we work with General Mills for their case conveyors and the robotic palletizer, right? And then there's one of their facility in the Milwaukee, and then they already installed a lot of IoT devices and security cameras, but still cannot, reduce their downtime. So we're working with them, and then to demonstrate this, the system is, and the second one is Aerospace Corporation. They have a laser processing characterization in the Southern California, right? So that's the welding facility. And then the Honeywell Corporation, they have also have another welding facilities to get how to improve their efficiency at the commercial aviation repair and overhaul. So this is in the Torrance of California. So these are the 3 demonstrations. Next, I think I'm going to share more details about the smart manufacturing for additive manufacturing, because we use one of the 3D printing use case. Initially, 4 years ago, we started working on this FDM 3D printer, the Stratasys U-Print. And then this is the overall one of my labs for the advanced manufacturing. So, but for this one, we have 3 use cases: robotics, 3D printing, assembly line. But today I'm shared in the 3D printing use case. So these are some of the the devices we use, and then we install inside of this room, right, to collect the data. And then like the smart meter we purchased from this company, and this is just some regular router, and then the cameras, the Intel RealSense, and this is another angle camera we placed inside of the 3D printer. So these are framework, right? I think we have 4 resources, like the internal camera to place the inside, and then the wearable cameras placed on the walker helmet, and then the global webcam to monitor the whole facility. And then we have the smart meter to monitor all the machines and devices inside of this large lab. And then we do the YOLO-based object detection, the craft-based test recognition, and we also the LSTM-based energy disaggregation to get each machine motion and the human action. So here, just show you one small demo of we build our web-based GUI to showing all the real-time data, right, from the video streaming, from the meters power information, and from the optimization, right? So for the instant replay, and this is the scheduling optimization for the facilities in these 3 use case. So here is our overall, the system architecture, like in details, because in the previous one, which is showing the results, the framework, right? So here we're showing how we can collect the data, right, from different resources, like the digital data that would be like a numerical data from smart meter. They're showing the voltage, the current, and the power. And then from the visual data, from the global camera, wearable camera, internal camera, and then we convert it to each frame, and then we process them, build the data. So you can see for the energy disaggregation, we did use the LSTM, the long short-term memory algorithm, to do the energy disaggregation. And then for skeleton, we do use the eBox that we showed you at the beginning, right? And then for the finger detection, the text recognition, we use a craft algorithm. And then YOLO, which is used the YOLO algorithm for the machine stage identification and object detection, because I will show you them all later. So here's all the workflow for the object detection. So it's the YOLO-based object detection. This is the like one example, the raw image, right? And then we process the image of the printer by labeling, right? And after do the labeling, and then we do the training. So here we can also, in the meanwhile, get the coordinates of the components in the pixel. So because the 2D image, they can give you the pixel information, but we developed this this is all the machine learning algorithm. It's pretty like basic YOLO object detection. I believe some of the students, you are pretty familiar with this algorithm. This has been widely used for the machine vision, and also for the driving. I think for some of the initial like autonomous driving, right? And then we collect the data, collect the images, and then we do the labeling, and then eventually we'll achieve like averages IOU is over like 92%. So we also do the projection. It's like from how we can get the accurate coordinates, X, Y, Z coordinates based on the 2D pixel image, right? And then get the converted to the 3D, the inches projection. So we call it the pixel inch projection. And then we calculate, get the really accurate one, because we want to know the location of these 3 components, like the build plate, extruder, and axle. So this is the another one is a craft-based text detection. This one was used for our AR system because the initially we found like for the object detection they can only detect the object, but how we can read these images, right? And then especially the text on the control panel. Because we build AR system and then we cannot real and then we cannot do the human machine interaction, right? So we find a way is one which still use the RGB change for your finger. Whenever your finger, the cover this button, right? And then we use the RGB image, you get the open pose, right? And then we know they have the RGB change, but for the text recognition, whether you press that button or not, right? And then we use the craft, right, to go the OpenCV to get the finger position. So here is another use case for the skeleton. So they got the RGB image, and then we use OpenPose to get the 2D skeletons, then filters, and then we can get the interactions. So these are the just different use case. And then this is the one for the energy disaggregation. We use initially we tried a lot of different algorithm, and then we compared, and then we realized we validated like a LSTM model, even it's an old algorithm, but it's really good, the effective one. So we adopt, and then we add stacked layers, extra stacked layers, and then improve the efficiency and the effectiveness. So it turns out really great. And then we also publish another journal in these areas, how to do the energy disaggregation based on the stacked LSTM model. So here is the, for after we, all these previous studies was, the done through our local, the high performance computer, this one, and also the cloud computing, the Nautilus platform. But then after we talked to the company in the locally, because for the field demo, we work with this large company, but for small company, they said they don't have these resources for cloud computing or the edge computing. So what they can do and then how they're going to perform that. So what we did is that we developed the affordable solution for the machine supervision. And then we just used like NVIDIA's Jetson Nano and Jetson Xavier. So initially, so because one is like only $100, another one is like $400. So we tried, without any supercomputer center, without any cloud computing. So just use the Raspberry Pi connected to the NVIDIA Jetson Nano, how many images we can process. So we tried many ways and then to improve the eventually, for the object detection part, I think we can achieve like 9 FPS based on the Jetson Nano. And then if we upgrade to the $400 Jetson Xavier, and then we can achieve like 26 FPS. So the processing is pretty close to the regular cameras resolution is like a 30 FPS, right? And now our lab is upgrading to the Jetson Orin. It's the most current one they released last year. I think it's $2,000 the GPU. So that one has way better processing unit. But this is the one like we developed for the local company. They are pretty happy about this one, and then we can still do without like any cloud computing connected to the local and supercomputers, right? And then they just use the Jetson Xavier and connect to the Raspberry Pi, and then we can still achieve a really good, the results. Like we also tested with different, got the left tilt, normal, right tilt, and then different condition of the light, like a working condition, interior light, exterior light, and then for normal tilt or on and off for lighting. So we all validate, that these are showing the accuracy, for these different scenarios. here I can show you the demo. Eventually, we just launch all the system, integrate it into our the web-based GUI, and then we can show you the real time. Like these are the 3 cameras streaming. This is the security camera. This is the camera placed inside of the 3D printer. This is the camera to monitor your finger operation, like on the panel. So here you can see the real-time detection for these 3 objects, and then to showing, we also build the mapping, and then to from the X, Y, Z coordinates, and then to figure out the machine state. So whenever you change the machine state, and then next one, I can show you the finger detection, the craft-based algorithm. So whenever, because sometimes it's hard to say, like you put the finger on the button, but you didn't press, right? So in this case, we can tell you whether you cover that and whether you press that button, because and then you can see whenever you press that button, this text label changed, right? And then here we can show you the real-time change right away, like yes or no and system setup, matching exactly on your real-time physical operation, right? So this is just some demo showing our system, how we are working. And then here is for the energy profile and this application. So we integrate all the informations and then from the smart meter and displays in the web-based GUI. And then as a user, you can just switch between all these different channels, because smart meter, they have up to 48 channels. So they can monitor each single channel, gather the device, like a plug-in device energy profile, and then they can get better, the results. So here is the instant replay, the demo that we did, like assembly line. We get one Alexa, Amazon Alexa voice control, right, on the assembly line. So whenever you notice any anomaly, right, on the assembly, and then because this is the small demo we did in the lab, and then we adopted to the General Mills manufacturing facility in Milwaukee, because that's really important for them, is how they can get the instant replay whenever they notice some anomaly, and then they can they can get the instant replay, and then they can do the investigation for their technical team. So there's another one. This is the AR system. This is the first version, like this is the digital twin version of our lab. In the one I showed, from this view, right, to showing the 3D printers, robotics, and then we get all the equipment placed inside of this room, and then build a digital model, right? And then here is the one we work with SimInsight, a company. They have a hyperscale system. So initially, version 1 is we just build the digital model and then put all the workflows, how to do the tutorial and the training to operate this 3D printer.
Operation. For the instructions. I hit next. Go on to step 2.
Can you hear the audio clearly?
It's in bits and pieces, so it's not very coherent.
Oh, let me reshare. Maybe I need to share some.
I can just start going through the instruction.
A little better now.
Yes.
I can just start going through the instruction operation, or the instructions. If I hit next, I'm going to step 2, or in step 3, and likewise
I can see step 3 on my scene.
Yep. So the instruction set is synced across the multiplayer room. So the first few steps are for uploading the file using a connected laptop. But we move on to step 5, we can start operating the machine. You can see here that the correct button is highlighted green. And so the same thing also shows up for Aruna. Is that right?
Yeah, I can see the last button highlighted green.
Yeah. And then if Aruna goes forward.
Yeah, I'll press on the next now. And that took me to step 5. That's on the machine highlighted as The second last button is highlighted green. Going to step 7.
Now it's the third button. So on and so forth.
And now I've gone to step 8. Yeah.
So all of these are the different tasks of the operation procedure. So moving the drive forward.
Yeah, I'm going to stop here. So this is the version 1 because we have more versions. From here, you can see they can only show you the procedures, right? All the tutorials, step by step. So whenever you mess up each step, and then they cannot tell you which button you pressed or which step you are located, right? So what we did is for the HyperSkills system itself, they don't have the object detection function. And then we build our own like algorithm and integrate to the system. So this is the demo, the version 2, like we can identify, right? For example, here is still, we use the Microsoft HoloLens 2, right? And then you can see they have 2. This is the virtual version of the machine. And then this is the physical classroom of their lab, right? And then, so whenever you press that button, then they can show you either like press standby mode or the maintenance, and then they can direct you to the right step or the next motion. So here, like I click, right? Your finger press that button, and then that says you press the maintenance. So because we use the YOLO-based object detection and the craft-based text recognition, right? Both of them to see you pressed and then also the text changed. So just the one small demo for the 3D print. And then here's another demo for the standby. Standby mode. Okay, you press the standby mode. Right. And then here's the version for the HoloLens 2. And then you can see how to turn the 3D printer on. Press the resume, and then they can click on the resume. Right, so they show you step by step, and then whenever you click on yes or no, and then they can detect you press that, right? And then you can go into the next step. So this is the demo they showed for the FDM 3D printer. So this one was done 2 years ago. And then last year we started adopted to the metal 3D printer. So that's why I'm going to show you another demo for the HoloLens. So we are working since last, I think it's the end of 2021. We started adopting the system we developed for the FDM Stratasys 3D printer to the metal 3D printer. So this is the machine in my lab. It's for the Renishaw AM400 is the laser powder bed fusion system. And then because you know that this is way complicated than the FDM, because for the FDM, normally I can train my students, right? But for this one, I need to hire the people from Renishaw. So come here, we paid almost 10,000 US dollars, right? For their traveling, for their training service, and then for 5 full days. So it's time consuming and expensive. So what we did is we want to build an AR training system for our students. And whenever I hire new assistant, and then we can train them, within shorter time, and also they can get all the knowledge from this AR system. So this is similarly, we adopt like the craft YOLO-based object detection, the craft, the text recognition, right? So this is what the like raw image frame, right? And then we convert to the grayscale and get the thresholding and then contour detection. So the craft mask, they will train, and then they can recognize your text region, right? Localize, and then they can detect this text, precisely. So this is the same thing, like we also build the digital model, like every single parts components in the, the physical machine, we just build them in the system, in the CAD modeling, and then including the machine itself, chiller, air dryer, argon tank, right? And vacuum. And also for the post-processing, including the safe station, including the cleaning station, the changing the filters. So right now I also have a group of NUS students. They are taking my new class I developed for the ME 6601. So they are working on another project for the Renishaw M500 in the AM center, right, at NUS. So that one is, I can show you one small demo. The student just sent me that short demo because they are going to make their presentation tomorrow. So I hope I can share all these more details, in the future, like full day workshop if we have. So here's just how we put all the training procedure and the flow chart into our, the hyperscales and the AR system. So this is the interface for the hyperscale. So this is the no-code 3D simulation software. It's pretty user-friendly platform. So you can just put all these different, like a title, instruction, the medium, right? And then you can put the step label, and then you can do the training, procedures, by step-by-step instruction. So here is the HoloLens we build into the HoloLens 2, and then for this machine, and then we trained, and then we also tested and validated. We did a lot of validation last summer, and then to make sure it's a robust system, and then they can detect your finger gestures. So this is the integration, how we do the integration of the AI text recognition object detection, because for this hyper scale system that developed by the SIM inside the company, they don't have the object detection function, right? They can only do the step-by-step, the no-code simulations, right? But they cannot recognize your objects from the HoloLens to a camera. So we integrate all the algorithm into this platform, and then we can identify all these different objects. So there's one demo of the metal 3D printer. It's also, let me show you. Me enlarge. So this is the one besides the step-by-step, and then they can also detect these object like handles, filter valve, right? Check the argon gas, the level, and then the air filters. So this is a virtual version. And we have another demo showing wearing the HoloLens 2 in the lab to physically operate the machine, and then show you step by step. And then I can show you another one. So this is the one they got to show, like locate the full size, do the wiper, right? And then move the wiper from one and to another, right? To collect the collection for the seed. So it's just one demo. Let me show you another demo, like the students just shared with me. This is for the machine in the NUS. So can you see this demo?
Yes, it's the keyboard.
Yep, the keyboard.
Okay.
Yeah.
Now you can turn on the 3D printing machine and your Python script to begin your study.
Yeah, so this is the a larger like industrial lab level 3D printer. The metal 3D printer is way better than the one I have in my lab. It's the AM400, but this is a RIN AM500M. Right, and then they build all the digital model from the lab and then do the measurements. So the students did an excellent job, for these projects. So this is the one you can detect the screen. Like here, they capture all these different screen panel, and then the AI system they can read and detect which text you get. So here you can performing the inference. So right now it's loading, and then like 30%, and then
You are at the build report
So
part
here-
now. You can select your 3D model file and check its report.
So this is just one demo, because after the presentation they make tomorrow, and then we're going to validate this new system for the 500M machine in the lab, and then we make sure they work pretty well, and then didn't have any errors or any issues. So here are some of the other the research what we did is that we also have 3 scenarios, like a baseline for all the lights on scenario, right? And then the low light scenario, right? And then you can see they detect pretty, the much really good accuracy, but the reflection scenarios, they have some errors because some letters was covered, by the reflection. So we didn't get really good trail. So we're still working on this and how to, build that. So these are also showing some of the results, for the AI text recognition and accuracy. So that's it for the AI part, how we'll use the smart manufacturing, right, to support and improve the, the additive manufacturing. So the next, I'm going to share pretty much the idea and the new project we are working now, and then because we don't have enough time, but I can share more details maybe in the near future for the full day workshop. So this is the one, like we're building the knowledge-based system to support the metal 3D printing, right? And then in that case, for example, for the new materials development, for the manufacturing process, the parameters optimization, right? And then even for like a metal powders recycling, right? So these are the 3 areas we're working now. So how we can build the AI agent system, right? And then to gathering all the information from the literature review, right? From the online database, from online information. So because of the the digital thread, AI machine learning, right? And AR, VR, metaverse, and also the advanced computing. So right now they get the new era, like technology convergence. So right now is able to create the metaverse. Like they have a lot of the, the potential applications, like in agriculture, in a smart city, and then you can do the predict, right? But for us, we are mainly focused on the manufacturing, especially in the 3D printing, the additive manufacturing. So here is one of the demo, like from University Chicago, the one PhD student, the demos. This was built on the Omniverse. So our students in the US were also building the NVIDIA Omniverse system, right? And then on the right side is you just use a camera to monitor in the real time, the facility for the lab. And the right side is the digital version of your lab. So you can see whenever they detect any motion of this component, and then they can simulate and then show you the exact movement, right, in your digital twin version of your physical system. right? So this is just give you the one demo, right? And then what's the capacity of Omniverse they can do? They can do a really good, the visualization, simulation, and they can also embed it like the AI processing and the prediction into your Omniverse. So that's just the demo of what we are doing now, like to implement into the metal 3D printing by leveraging the AI and the Omniverse system. I think I'm going to stop here. If any of you have more interest, and then I can share, the whole slides, and then you can also talk to me later, send me email. So this is the system. Like right now, we are partnering with NASA JPL. So with Dr. Ed Cho, he's the civil program manager. They built this system for the Audrey. It's called Audrey. It's a system for understanding the data through the reasoning, extraction, and the synthesis, right? So from how to process all the different data, then get the processing the front end, to do the neural network, right? And then to do the learning and the reasoning. So the stuff is for us, we are mainly focused on these two, like multi-domain representation learning to automatically build the knowledge graph, right? And then the second one is how do the differentiable reasoning to grow the knowledge, right? Because for example, for the metal 3D printing, we have done a lot of work, we're pretty familiar with stainless steel, right? And then to do the processing and then the design and applying the support, right? And then the parameters. But now we're developing for the new materials like nickel, right? From nickel to Heinz 282, like the one we're doing in the lab. Or even like for the most difficult, like copper or tungsten, how we're going to optimize and then these parameters, right? And then how we can learn from other, the literatures, like papers, already published papers. So that's our focus. Like we use right now we're all group of students that are also testing like OpenAI GPT, ChatGPT, but we also right now using the GPT 4.0 and the Google BERT, right? To extract the context and the knowledge, build the knowledge graph, the graph database, and then also we use Apache Tika. We can support a lot of documents and formats, from text, from CAD model, from like video, image, audio, and then all these different the formats. So same thing, we put them into the Omniverse, because the Omniverse is based on the USD platform, right? Universal Scene Description, so they can accept the cross platform, the software tools, and then to do that. So this is the one, like we're working on the metal 3D printing, especially for the laser powder bed fusion. Like right now we can use E-beam, right? We can get the X-ray images, right? To show in the real time, the monitoring. But how we can get all these informations, like external multi-domain data resources, and then build the knowledge graph, and then from each domain, right? And then how to get the reasoning across these domains, and then to get a better like AI agent owners, right? For example, how you're going to build this organic, the generative designs, the structure, right? For the aircraft, the components, working with NASA, because this is the project we're working with NASA JPL, NVIDIA, and Amazon for this project. So this is the mainly focus on the AI agent, the platform and the tool for the additive manufacturing. I think that's it for my presentation today. Sorry, I have a little bit running out of time.
Thanks so much, Prof. Lee. We have a couple of minutes for questions. So if you'd like to unmute yourself, we'll stop the recording at this point.